Welcome back to our AP Chemistry notes over titration. Previously, we used a rice table to look at how much salt would be produced or how much acid or base would be left over, and that really was a neutralization question. We really had not gotten into titration yet. With the titration, we seek to answer a question more like this. What volume of hydrochloric acid would neutralize this volume of calcium hydroxide? So we're really going to now get into some true titration, that is, using a known acid to find out information about an unknown base, or using a known base to find out information about an unknown acid. That is a true titration that's going on there. You most certainly could do this in a rice table, but that would be, in my opinion, a little more work than you need to do. If you have a titration question, it would work just as easily to put it in a railroad track. And so I want to demonstrate that. First, I want to focus, and to focus, I have my written balanced equation. And this is how it would work. I'm starting with my molarity. And I like to start with the molarity, and you, of course, start with the molarity of the one you know about. So I'm going to start with my molarity. And I'm going to turn that into moles, because our railroad tracks only work in moles. Our equation, we can only use the coefficients of our equation when we're talking about moles, so at least for railroad track. So we're going to turn, notice how I turned my molarity into moles per milliliter. I mentioned at the beginning of the last video that that's a great way to start. And I'm multiplying by my milliliters that I used. So I've used 30 milliliters. And please check this out. I use 30 milliliters of this much calcium hydroxide. My known is actually the second thing listed in the question. Don't let that throw you. It's what volume of acid. That's what I'm looking for. Here's what I know. I know a complete set of information for the base. So I'm going to start with the base. So please pay attention to what you know and what you don't know information for. So milliliters are going to cancel there. I have moles of base. Now from my equation, I know for every 1 mole of calcium hydroxide, I will neutralize 2 moles of hydrochloric acid. So I have that information there. And then moles of calcium hydroxide cancel. Now I have moles of hydrochloric acid, and I'm looking for volume. So if molarity is moles per liter, and I'm looking for the liters, the volume, then the volume is moles divided by molarity. Okay. Well, I already have my moles. Here I'm going to divide by my molarity. But I wrote molarity as moles and milliliters, very similar to over here, so that you could actually see how moles of hydrochloric acid cancel, leaving me with milliliters for my answer. Now I did not have to put milliliters here. I could have put 1 liter, and then my answer would have been 0.0200 liters. And that would, unless they specify, that would be just fine. I just think since we're given milliliters in the problem, we should say milliliters. It was a personal choice there. If they ask on the test specifically what volume in milliliters or what volume in liters, you better answer specifically or you're going to miss the point, because then you're just not answering the question. So be sure that you read carefully what it is that they're going to, what it is they want you to answer. And if not, you have your choice. What you could not say is you get 20.0 liters. That would be incorrect. What you could not say is to have 0.0200 milliliters. That would be incorrect. 20 milliliters or 0.020 liters, maybe another 0 there for sig sake, that either of those would normally be acceptable. So that's how we do it. Turn my molarity into moles per liter and multiply by my volume. That left me with moles. Did my mole ratio, just like we did a gazillion times in pre-AP, and then turn my moles back into volume by using my molarity. Notice how it's a molarity, it's just inverted. Okay, I flipped molarity. Instead of moles per liter, it's liters per mole. And my railroad track told me to do that. I didn't even have to think about that. To get moles to cancel moles, that's the way I had to write it. Okay, so I want you to pause and try to work this out. Again, you probably want to do a railroad track. You could use a rice table, but it, in my opinion, is the long way around. So pause the video now and come back in a few minutes once you have done the work. And if you're thinking, oh, I got this, I'll just watch the video. No, you don't got this. And you can prove it by trying it. And if you don't try it, then you're just being a chicken and you're only hurting yourself. Because come test time, what you think you got and you don't got is what you're going to lose points for. So pause the video now and come back once you think you have an answer. Now first off, I like to focus by looking at the reaction. I have acetic acid, and if you don't know by now, acetic acid is acetate ion with a hydrogen, and it's mixing with barium hydroxide, and it's going to make, and again one-way arrow, it's going to make, oh, I feel like writing the water first, and then barium acetate, and new compound, new crisscross. Okay. Now I actually need to go through and I need a balance, so I'm going to need a 2 there and a 2 there. Okay, now I have a great reaction. Now I am focused. Now I ask myself, what do I want to know? Or I ask myself, what do I need? Or what do I have that to find what I need? So I'm looking for what volume of acetic acid. So I want what volume, that's a liters, of acetic acid if I have 18.7 milliliters of 0.0105 molarity barium hydroxide. And I note over here, I do know it's a 0.1050 molarity acetic acid. Okay? So that's what I've got going on, and the question you need to ask yourself is, what do I have complete information for? There he is. That's what I have complete information for, so that's what I'm going to start my railroad track with. 0.105 molarity. Oh, no. Let's write that as moles per 1,000 milliliters. Great way to start the problem. Yeah, I know it's kind of like wrong to start your word moles with a capital M when that's what stands for molarity, but you see it's a way to get my problem started. Okay. I have milliliters I want to get rid of, so I need to know milliliters. Hey, they told me 18.7 milliliters. So now milliliters cancel, and I've got moles of barium hydroxide. And you might want to label it, BaOH2 or something like that. That's up to you, but don't get confused by all the moles that we're going to have running around. Now that I have moles of barium hydroxide, I know I need moles of barium hydroxide down here. Imagine that. Labels match diagonally. I'm looking for acetic acid, so let me throw in some moles of acetic acid right here. And what do I put here? Oh, you're right, the mole ratio, one of those to two of those. And now moles of barium hydroxide have canceled. And to answer the question, I need a volume. Well, I know I'm going to want moles of acetic acid down here. And if I'm wanting volume, I could put liters, but you know what? Let's put 1,000 milliliters here. Okay, because again, I could do moles per liter or moles per 1,000 milliliters. And the concentration they told me of the acetic acid was 0.0150 moles per 1,000 milliliters, moles per liter. However you want to phrase that, but just be sure you know what your label is at the end. Okay, so now that we've got that all laid out in the railroad track, it is super fun. Calculator time. Yay! I know you every day look forward to, oh please, can I pull out my calculator and calculate some railroad track? I do point this out. The 1,000 here and the 1,000 there will cancel. So that actually helps me get my answer a lot faster. I'm going to take my 0.0105 and I'm going to multiply by 18.7 and I'm going to multiply by 2, and don't say divide by 1 in your calculator or you're just stupid. Save yourself that time. Thank you. And I'm going to divide by 0.0150, and the number I get from my calculator, and I see 3 sig digs, 3 sig digs, 3 sig digs. So let me go to 3 sig digs. I get this random number of 26.2. Okay, that's a 2, by the way. 26.2. Well, lottie freaking da, what does that mean? Well, check out the label that hasn't canceled is milliliters. I know the number. I got scratch happy, sorry. The number 1,000 canceled, but the label, this label here did not. So it's 26.2 milliliters. And that's fine. Also acceptable would be 0.0262 liters. Don't ask me in class if you could have it in liters instead of milliliters. Okay? Dumb question now. Yes is the answer. Now you know. Unless they specifically ask, unless they specify, you need to be sure that you match what they ask for. Otherwise, you can have it either way. Okay, so that's another way of how we do neutralization, and this would be more like an actual titration, using complete information of a known to find incomplete information of an unknown. That is key characteristic of titration, and that's why we do titrations, to find unknowns. So a titration is adding a known solution, often called a titrant. So that's the one we add to an unknown solution to determine that unknown solution's concentration, or we could determine the volume if we wanted to, but I mean normally we pour that into a container and we're like, oh look, it's 53 milliliters. So it's typically we want to know that unknown concentration. We, before titrating, will often need a standard solution. A standard solution is used when we titrate one solution with another to get the exact concentration of the titrant, so that we know when we go to use it later what it really is. And you're like, why is that? Well, okay. So check out our common acids and bases, the ones we normally would like to use, they tend to decompose. Or they also tend to become contaminated as they sit in the storeroom. So I have a bottle. Don't know why that popped up. I have a bottle. Well, I thought I had a bottle. I have a bottle. There's a screw lid, and now it looks like a cylinder, right? I have a bottle of, say, NaOH sitting around. It's liquid. It's a solution of NaOH. It's sitting around the storeroom, and it's not used for years. Okay, it does last a while on the shelf, but not perfectly. So eventually this is going to decompose. Well, if I'm expecting it, because I made it, let's say 10 years ago, I made it to be 1.5 molarity. And I come back 10 years later, and I'm still planning to use it, but now in reality it's 0.9 molarity, but I'm calling it 1.5 molarity. My results are going to be about half as good as they should be, because I am assuming I have 1.5 molarity when I don't. So this is a very, very common situation, especially with hydrochloric acid and sodium hydroxide. They do decompose over time, and most certainly in a storeroom there's a good chance it can be contaminated with other stuff floating in the air. So what we do is we standardize it. We titrate what we want to use to titrate. We titrate our titrant with a standard. And once we do that, it would have been clear to me that that would be not the 1.5 I thought it would be. So that's how we prevent that issue from arising of making the error, oh, I thought this was 1.5, it's only a 0.9. If I standardize it, then I would know, oh yeah, this is now 0.9, let me change the label. So typically, check this out. If we need to standardize an acid, well, we're going to standardize an acid with a base. And the base we typically use to standardize an acid with is sodium bicarbonate, otherwise known as baking soda. I would, dissolve some in water, a known amount. I would make a molarity solution, and I would know that. But I could make that solution. Again, here's my bottle now of sodium bicarbonate solution, and that can sit on the counter for like 10 years, and still, if it started at 1.5, even after 10 years, it would still be like 1.5. It decomposes extremely slowly. So that's a good choice for standardizing an acid and being sure that it is still what I think it is, or letting me know that it's not. What if I want to standardize a base? Well, I would want to use an acid. And the acid we use for it is potassium hydrogen phthalate, otherwise, as you will appreciate, known as KHP. Because I'm sure you don't want to go around having to say potassium hydrogen phthalate every time that you want to talk about, hey, who's got the bottle of potassium hydrogen phthalate? Hey, have you seen the potassium hydrogen phthalate? I don't know where it is. Oh, there it is. I think the potassium hydrogen phthalate's over there. Okay, so we call it a KHP. And the point is, again, I can make up a solution of KHP, and it can sit in the stockroom for a long, long time and still not decompose. It is more likely that the potassium hydrogen phthalate and the sodium bicarbonate are not decomposed compared to our normal acids like hydrochloric acid and sodium hydroxide for a normal base. So I'm going to use a very, very stable base to standardize an acid before using it to find an unknown base. And I'm going to use a very, very stable acid, like KHP, to standardize a base before using that base to find my unknown acid. So I know it seems like a weird roundabout way, but it really is the best way to reduce error in a titration lab. Because as we do our titration, I've got the burette, and it's dripping into a beaker. And I'm controlling how fast it's dripping, and I'm swirling and all that. If I think my titrant is 2.0 molarity, but in reality it is 0.5 molarity, everything I calculate for that unknown is going to be wrong. I don't want to go there. Now maybe we're lucky and we think it's 2.0 molarity and it actually is a 1.9 molarity, and then we're okay. But how do we know that that's the case, whether it's this case or that case? We don't know until we use our very, very stable acid or a very, very stable base to say that it is still the amount we think it is, or here is the new amount, and we use that. It is not uncommon when I go to conferences and trainings that we do a lab like this, that the presenter asks the student at the university to supply a 1 molar solution of sodium hydroxide and then to supply some KHP. And we do our standardization and find that nope, it's not 1 molar. In fact, it is 0.9997 molar. And I know you're like, oh, well, that's easy enough to call 1. You're absolutely right. I would not hesitate to call that a 1 molarity. That is awesome. But what would happen that one time that we're expecting it to be 1 and it comes out to be 0.09997 molarity? Now we're at a tenth the concentration we thought we'd be at. So very, very important. And if you're given a lab-based question this year, because I don't know which one they're going to pick. I know there will be a lab question this year. I just don't know which one they're going to pick. It'd be very, very important if you're working with a titration situation that you state somewhere that you are standardizing your base or that you're standardizing your acid. Whatever is your known, you need to standardize it before using. It'd be awesome to be able to say that you use sodium bicarbonate or KHP. More than likely, they would even list that in the materials list. Even if they don't, you can probably get away with saying, be sure you standardize your acid before using it in this way, or be sure to standardize your base before using it in this way. You can probably just say that and get your points for that. So that is our habit. We're going to standardize, and before we do our lab in class, we're going to standardize as well. But moving on, I want to talk about more titration stuff. We have the equivalence point. Please catch this. These two, most students think are synonyms, that if you know one, you know the other, and that is so not the case. Please, 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 please note the contrast, the difference between these. At the equivalence point, you know your concentration of acid exactly equals your concentration of base, and typically that's hydrogen ion and hydroxide, because we're using the Arrhenius definition. The end point is when the indicator changes color. Notice I did not say anything about any concentrations of anything being equal to anything. I've just simply said if you know the endpoint, that's when the indicator changes color. That's all you know. Your hope is that you pick the right indicator so that your endpoint and your equivalence point match up, but they don't have to. Okay, for instance, one of our most common indicators, phenolphthalein, changes around a pH of 8. So before pH of 8, it is clear. And after, that's clear by the way, after pH of 8, it's a pinkish purple. We say pink, but honestly, it quite often can look purple, especially if you use a lot of it. And that happens right at 8. So it's like clear, 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 clear. Oh, we hit 8, purple, 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 purple. What if my equivalence point should be at 4? This isn't going to help me. It doesn't do anything till I hit 8. What if my equivalence point is at 11? Well, that's not going to help me. It changes at 8. So that's why we have lots of indicators, so that we know which we can like pick our indicator, tailor our indicator to where we think approximately our equivalence point's going to be. Because without equivalence point, we can't calculate a titration. Here's something important to lodge in your head. The pKa of the indicator should be very close to the pH of your equivalence point. And then you know, and I'll mention this in later videos when we get back to titration curves, okay, with strong acids, weak acids, triprotic acids, all of that's fun stuff. I'll talk about this again. But this is how I would pick my indicator. I would go to a big chart of indicators and I would look and I'd be like, oh, if I think my equivalence point's about a 4, I would look for something with a pKa of about 4. And if I need something at 7, I would pick something that has a pKa of about 7. Phenolphthalein works fairly well. We will discuss if it really is a big difference, whether that in between 7 and 8. Is that a noticeable difference in your calculations? We'll discuss that later. Okay, if I need something around 11, I would look for something with a pKa of around 11. So you want to tailor your indicator to your situation. Okay, with that said, examples of titration reactions. What is the molarity of the hydrochloric acid if it took 36.7 milliliters of hydrochloric acid and we titrated that with 43.2 milliliters of 0.236 molarity sodium hydroxide? Okay, so again, what do I know complete information for? I know complete information for sodium hydroxide. So I have 0.236 moles per 1,000, because that's the way I like to roll, 1,000 milliliters. And I used 43.2 milliliters of that. Oh, look, milliliters cancel, and I have moles of base. The sodium hydroxide is my base. I'm just going to write it that way. And according to our balanced equation, 1 mole of base is 1 mole of acid. So 1 mole of base can neutralize 1 mole of acid. And now I have moles of acid. Well, I want to go from... Oh, I don't have the molarity. Did you catch that? What do I need to find a molarity? I need a moles per liter. Oh, hey, let's check this out. I'm not going to continue the way I was because that's not going to give me what I need. I'm going to stop and calculate right now. And I'll point out, why did I stop and calculate right now? Because the thing that hadn't canceled is moles of hydrochloric acid. And that gets me half of what I need for molarity. So knowing when to stop your rototrack could be half the battle. Okay, so I've stopped my rototrack when I've gotten moles of hydrochloric acid. Okay, now that I know moles of hydrochloric acid, to get moles per liter, and I just multiplied. And it's okay, and I wanted to demonstrate you get the same answer if you do your volume then times your molarity or molarity times your volume. That shouldn't matter. So get over that. Now that I have my moles of hydrochloric acid, to find molarity, I just need moles per liter. And you're like, whoa, 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 where did that come from? Well, that actually came from right here, from the problem. I just turned it into liters before using it, and I plug these numbers into a calculator. Okay. So knowing what you need to find out will tell you when you need to stop your railroad track. And this was a case where we needed the molarity, so I need first the moles because I already knew the volume. I could just divide then the moles by the liters. So don't think it has to be a huge long railroad track when it does not have to be. Okay, so your turn. Let's give this a try. What's the concentration? Oh, that'd be a molarity. If that many milliliters of that much molarity base was neutralized by that many milliliters of acid. Okay, yes, you're supposed to pause it and try it. So prove it that you can do it, pause it, and try it. Okay, welcome back. You should have paused it. If not, shame on you. You're only hurting yourself. I get paid the same either way. This is for your benefit. So pause it and do it if you haven't. I have complete information for my base. But you know what? I want to focus by writing my balanced equation. Okay, so there's my balanced chemical equation. Now, I want to start with my given information, and I just feel weird, so let's do it this way. 43.2 milliliters. I use the volume first. I can do that. 0.236 molarity. Nope, that's not molarity. That's a moles per 1,000 milliliters. Do you like the way I kind of like pull that out? Okay, I know you don't care. But that's the way I do that, because as I write molarity out of copying, I'm like, oh, wait a minute, I want to expand that to moles per milliliter. And so that's the way I write it, and it works well. And that's of my base. And for my balanced equation, 2 moles of base will make 1 mole of, or will use up or neutralize 1 mole of acid. So now milliliters are canceling milliliters, and moles of base is going to cancel moles of base, and I get moles of acid. And it is that ever fun, popular calculation time. Yay! So, being careful to read my own writing, 43.2 divided by 1,000 and times a 236 that was, and dividing by 2. And I get that I have 0.0050. I'm going to leave it as 98 for now. What's my label? Moles of acid. Does that answer my question? No, I was looking for concentration. So I'm going to divide that by the liters of solution. How much liters? 0.0367 liters. Now moles per liter is molarity, so I need to take the number I just had and divide by 0.0367. And here is my official answer, 0.139 molarity of acid. Okay, so that's what that concentration of acid was given that information for the base. And that's the power of a titration, to find the unknown amount of acid with a known base, or reverse that, find a known amount of base with an unknown acid. Okay, last thing I want to mention is you might hear rumors, and I hope it's just rumors, you will not find it on the AP test, of this thing called a normality. Do not think that they are saying molarity just in a weird way. They are not. Normality is a very different thing than molarity, and honestly it sucks, which is why it's off the AP curriculum now. Normality tells you not how much acid will neutralize base or base will neutralize acid. It tells you how many equivalents of acid would neutralize base or base would neutralize acid. Does that sound confusing? It's not confusing if you're doing qualitative work. It is just fine if you want to compare, is this a stronger acid than this one? Is this a weaker base than that one? Normality would work great for that. There are people who get these big shipments of milk in from dairy farms, and they need to test before they accept the milk if the milk is fresh enough for them to put in and bottle and, put on store shelves. Because if it's not fresh enough, they don't want to accept it, because what are they going to have to do to it? If they accept it, they pay for it, and if they can't use it, if it's already gone bad, they're going to just have to dump it. So there are people who actually just sit there and do nothing but test milk for freshness all day long. The normalities would work great there, because it's just a comparison. Yes, this is fresh enough to process. No, this is not fresh enough to process. That's all they need to know. What it's not good for is when you want to calculate the amounts of an unknown thing like I just been demonstrating. So that is normality. You'll not see it on the AP test. It's not in the curriculum, and for good reason. That's not to say it doesn't have some useful purposes. So if you ever hear someone talking about normality, they're not butchering the word molarity. They're talking about something different. And the way normality works is you get equivalents. So one hydrochloric acid gives us one hydrogen ion, so that's considered one equivalent. But sulfuric acid gives us two hydrogen ions, so that would be considered two equivalents, or a normality of 2. And one sodium hydroxide gives us one hydroxide, so that's a 1 normality, whereas a calcium hydroxide would be a 2 normality. So it is weird, and it doesn't serve great calculation benefits, but certainly if you're just wanting to know, hey, is this unknown drink neutral enough to drink and not hurt us? Well, you could certainly do a normality and be like, oh, well, it's less acidic than a Pepsi, and so therefore I can drink it. I don't know why you'd want to do that, but that's what normality would do for us. Just let us know, is it less than this amount? Is it more than that amount? It's great for qualitative work. We're not going to use it because we want to do quantitative work, and your labs are going to be quantitative work. I do want to introduce the vocabulary to you, so if anyone starts talking about it, you know exactly what they're talking about and why it just really is not all that useful. Okay, well, that's the end of this video. I know it's been a long one, but you have some calculations to practice and a lab to get ready for. So good luck.